Video 2 in the series of rates videos. I want to now get into the practicals and how we monitor reaction rates in real experiments. We covered the theory last time. So moving on to practicals, how might we monitor and follow a rate of reaction during a reaction experiment that's going on? Well, we've got to find some property that changes. Like, say the colour changes. Well, we could monitor the colour change. If gas is coming off, we could monitor the volume of gas coming off. If some chemical is being lost, like a gas, then we can monitor the mass of the chemicals as the reaction proceeds, etc., etc. We must find something that changes as the reaction happens. Now, to follow the rate of reaction, we must measure something that changes. There are a number of useful ideas. Volume of gas, and measure it at regular time intervals. Measure the mass loss of a reactant at regular time intervals. Measure the mass gain of a product. If it's a product, they will increase in mass at regular time intervals. Measure the time taken for a cross to be obscured. And all of these you need to know about within GCSE. So, the apparatus setup. I am going to be showing you these experiments. Marble chips in dilute hydrochloric acid, they will fizz. And as they fizz, the fizzing is gas bubbling out into a measuring cylinder. That's how you practically measure the volume of gas coming out in a school laboratory with a whole class load of pupils. This is how the teacher might do it. Gas syringes are expensive. If you put a gas syringe on the end, then any gas coming off will push the syringe out, and you'll measure the volume of gas coming out like that. But essentially, measuring the volume of gas coming off. When I got these images off the internet, they're not quite what I wanted, because you measure the volume of gas coming off in a time frame. You have to link it to time. And therefore, if I was doing this, I would take the volume of the measuring cylinder every 10 seconds. If I was doing a gas, I would take the volume every 10 seconds. And then you would plot it on a graph paper. How about this one? I think my first practical I have lined up is to do this. Apparatus setup with large marble chips and small marble chips. But when I do this kind of setup, and I'm measuring on a balance what's happening to the mass will go down, and I would measure the mass every half a minute. And then again, I'd then have results to plot on a graph paper. Sodium thiosulfate. Sodium thiosulfate reacting with acid will produce sulfur. If we put a cross on a piece of paper, I've got a cross on a piece of paper, and put that piece of paper underneath our reaction vessel, then the solid that's made, if I look through the top, I will be doing this practically, you'll be able to see in the video. Measuring the time it takes for a certain amount of sulfur precipitate to be made, which will obscure the cross. When the cross is obscured, then you take the time. Time how long it takes to obscure the cross so that you cannot see it underneath. Okay, so they're the ideas. Those ideas are different ways of monitoring the rate of reaction. From here onwards, I get into some real experiments. So the first real experiment I'm going to do is marble chips. Calcium carbonate. One form of calcium carbonate is marble, If we have chips of marble, there'll be this chemical. They'll react with hydrochloric acid. Acid and carbonate make salt, water, carbon dioxide. You should have learned that as one of our general equations. And marble is a form of calcium carbonate. We use large marble chips. We're going to use large marble chips, and we're going to compare them with same mass of small marble chips and monitor the reaction using balances. Since the mass of the reaction vessel decreases, the reaction proceeds. The rate of decrease, the rate of the mass going down is a measure of the rate of reaction. There, we're going to do that. Right, let's pause it there and show you that being done. Hi, so two balances, piece of paper on there, piece of paper on there. Tear the balances. Tearing sets them both to 0. I've got some big marble chips. That many. It's about 7.51 grams. Of large marble chips. Here I've got small marble chips. It's labelled calcium carbonate because marble is the metamorphic form of calcium carbonate limestone rock. Now, carefully, if I try and get the same quantity, 7.51. .3, I've got a little way to go. 7.08, get in there. 7.7, takes them out. 7.57, takes them out. 7.5, there we go. Perhaps one more grain out. If I just get these together, just wipe away anything that might be on there, and take one more grain out. There we are. So, hope you can see that. Both of them are 7.5 grams. Now, the comparison is only valid if you start with the same mass of both. Remember the fair test ideas from general science? That when we're comparing, we must try and keep as much as we can the same and change the only thing that we want to change. So the only thing I want to change is the size of the lumps of marble chip. And they're small here and large there. I want to try and keep everything else the same. So I've got 75 centimetre cubes of acid there and 75 centimetre cubes of acid there, and the acid is hydrochloric acid from this bottle. And I'm going to take these lumps and put them into the acid, and I'm going to take these lumps and put them into this acid, and then I'm going to look at reaction. I expect to see a faster reaction with the small lumps. Can you see that? I expect to see a faster reaction with the small lumps, and I expect to see a slower reaction with the big lumps. If I follow it on the balances, then I expect the mass to go down faster with the small lumps. I expect the mass to go down slower with the big lumps. Now, there is something you need to be aware of. You need to be aware of the idea that we need cotton wool. And when these reactions take place, you will see that there'll be fizzing. And I don't want the fizzing to be shooting out bits or spitting bits of hydrochloric acid out of the flask. So we put these things, cotton wool, into the neck of the flasks. They will let any carbon dioxide gas that's made out, but they will stop any spits of acid from spitting out of the flask, which would mess up our results. So we're going to put those in, and I'm going to, it would be nice if there were two of us, we could do it at the same time, but there aren't, there's just me. And I'm going to just put this in, try and do it together, and then I'm going to tare both balances. Tearing means set them to 0. So let's just try and get them both in together and set them to 0, and then we can watch the mass decreasing. 3, 2, 1. Oh. Cotton wool, cotton wool. You can see the reaction. I'm tearing them. You can see the reactions. Much more vigorous reaction going on with the smaller ones, and much slower reaction going on with the bigger ones. Can you see that mass loss in the balances? The mass loss of the smaller, this one, it's lost 0.23 oh, I think that's just me leaning on the bench, but the mass loss here is more. The mass loss there is less. Visually, if I show you, you can see that is much more vigorous with the smaller marble chips than that is the bigger marble chips. This smaller marble chips has lost now about half a gram of carbon dioxide has been formed and has left as a gas. This one, 0.04 grams of carbon dioxide has formed and left in a similar time. So this is much faster reaction. Why? Because for the same mass, you had a lot more surface area. A lot more surface area where the acid could collide with the marble chips and make reaction. Now there are two ways to do a graph of this. One is you plot mass loss. The other is you plot the mass of the apparatus. And mass loss will give you a curve which is that way up, and mass of the apparatus will give you a curve which is the other way up. I'll show you in my PowerPoint. But I hope you understand the basic idea of comparing size of pieces, such as large marble chips and small marble chips, with each other. And I hope you understand the idea of surface area, how the surface area will affect the speed of the reaction. The more the surface area, the faster the reaction. Therefore, the smaller the pieces, the faster the reaction. And let's have a look at some graphs on my PowerPoint. That was the apparatus setup that I showed you. I hope it was clear. Small marble chips react much faster than large marble chips. And if you were to plot it, say you had a balance that didn't have a tare button, and all you could do was measure the full mass of the acid inside the conical flask and the cotton wool bung. If you did that, you'd get a graph like that. It would have that shape. It would start off at a high value and it would come down. It'd come down as carbon dioxide was lost, and eventually it would become flat at the end. The flat at the end is when the reaction has stopped. So the reaction happens and stops, and the mass goes down as the gas is lost. So that's not mass loss, that's just mass of the apparatus. Well, another way to do that is to look at mass loss, which is what I was doing. I tared both balances to 0, and then as the gas left, I got a negative value for mass. That was how much mass was being lost. Now, if you plotted just the mass lost, then you get curves that are not that way, but that way. You get those kind of curves. And either way, whatever they give you, I want you to be able to understand it and answer questions intelligently about it. If you had mass loss and you got those curves, like the blue one would be if you had small marble chips, and the red one would be if you had big marble chips. The red one is a slower reaction, the blue one is a faster reaction. Can you see the blue goes flat earlier? The blue goes flat earlier than the red goes flat later. The blue is a faster reaction, the red is a slower reaction. Label time, loss in mass in grams, etc. You need to be able to deal with whatever they throw at you. So whether you get that kind of curve coming down that way, whether you get a curve going up that way, it's for the same experiment. Depends how they present it to you, and you know what's going on, and it's all to do with size of pieces and surface area. Now, because that apparatus was giving out gas, there are other ways to collect gas. And I just wanted to run through this without doing the practical. But say you had magnesium. That's another solid, metal, reacting with hydrochloric acid and not marble chips. Then, if you had magnesium in there and you wanted to measure the volume, then you could have that apparatus or that apparatus. You're more likely in school to have that apparatus and your teacher to demonstrate that apparatus. But either of them you need to be aware of in an exam, can be set, and they can be used wherever there is gas coming off. So you can monitor the gas coming off and you would get curves like that. Or volume of gas, that would be. Volume of gas. Like that. And like small pieces of magnesium, big pieces of magnesium. The curves on the gas would be this. I'm getting tongue-tied. The curves would be similar shape. Say you were measuring the apparatus mass, then even with magnesium, you get a very similar shape. I think I'm repeating myself, I'm sorry. So, if you had volume, you might get curves like that, where you're measuring the volume of hydrogen gas that's being given off. The volume given off every, what's that, every 10 seconds or so? And the red would be like, if you had double, 1, 2, 3, 1, 2, 3. If you had, red would be like if you had double the amount of magnesium compared to the blue. Or the red would be if you had more acid and it was the acid that was the limiting reagent. If you had double the amount of acid, then you get double the reaction. That's double the reaction of that one. You've got to pay attention to moles ideas in this section too. Right, so I'll stop there because this next practical is a big practical. I'll deal with it next. I'm going to stop it there.